Hello students, welcome back to module 1 of basic electronics. In this video let us discuss multivibrators. The name itself says it is a vibrator multi. You know the meaning of multi and also you know the meaning of vibrators. So multi-vibrators. In the previous video we have discussed the oscillators, the Wien bridge oscillator which generates the sinusoidal waveforms. But there are many occasions when we require a square wave output. There are many occasions where we need square waveform also rather than a sinusoidal waveform. The multivibrators are a family of oscillator circuits. These are also oscillator circuits that produce the output waveforms consisting of one or more rectangular pulses. There are three types of multivibrators. The first one is a stable multivibrator. A stable, or few people they call it as astable multivibrator that provide a continuous strain of pulses. The other name for a stable multivibrator is the free running multivibrator. Then the output waveform will be a free running or continuous strain of pulses. So something like this. Next, monostable multivibrators. Stable multivibrators that produces a single output pulse. That means they have one stable state. And are thus sometimes also referred to as one shot. Monostable. This state is stable and one shot it will go to the high and it will come back. Monostable, a single stable state. The third one, the bistable multivibrator. Bi means two. That have two stable states and require a trigger pulse or a control signal to change from one state to the another state. So it will have one state. Then if you apply a triggering pulse, it goes to the second state. Then it will be 0. Then if you apply a triggering pulse, it goes to the high state. So bistable multivibrator. There are three types of multivibrators: stable, monostable and bistable. The term multivibrator simply originates the fact that this type of waveform is rich in harmonics. Multivibrators use positive feedback. Whenever you hear oscillator, remember the positive feedback. Amplifiers use negative feedback, oscillators use positive feedback. Multivibrators are family of oscillator circuits. So multivibrators use positive feedback. Let us see the single stage astable multivibrator. Astable means, as you know, it produces a continuous strain of pulses or a free running multivibrator. Let us check how this generates the continuous square waveform. A simple form of a stable oscillator that produces a square waveform output using the operational amplifier. Inverting input terminal, non-inverting input terminal. Some portion of the output is fed back through the resistance R and also through a voltage divider R1 and R2. A positive feedback with the output fed back to the non-inverting terminal through the potential divider formed by R1 and R2. And here is a capacitor C. This circuit can make a very simple square wave source with a frequency that can be adjustable by replacing R with a variable or preset resistance. If you use a variable resistance instead of a fixed value resistance, you can vary the frequency also. So now let us come to the working of this. Initially, let us assume the capacitor is uncharged and the voltage at the inverting input terminal is less than the voltage at the non-inverting input. Remember the comparator circuit. Now here I am saying the voltage at the inverting input terminal is less than the voltage at the non-inverting input. So the output voltage will be plus VCC because the voltage at the non-inverting terminal is more than the voltage at the inverting terminal. We have assumed capacitor is uncharged, so voltage at the inverting terminal is less than the non-inverting terminal. As the voltage at the non-inverting terminal is more than the inverting terminal, the output voltage saturates to plus VCC, As the output voltage is at plus VCC, now the capacitor starts to charge, in this direction. So the upper plate of the capacitor becomes positive, the bottom plate will become negative. The capacitor C charges through the R. If it is charging through the resistance R, the capacitor charges exponentially. The voltage at the inverting terminal, starts to increase. As the capacitor is getting charged, the voltage at the inverting terminal starts to increase. If the voltage at the inverting terminal crosses the voltage which is present at the non-inverting terminal, I repeat, the voltage at the inverting terminal, if it becomes more than the voltage at the non-inverting terminal, now the output voltage changes to minus VCC, as the voltage at the inverting terminal is more than the voltage at the non-inverting terminal. It becomes minus VCC. The output voltage rapidly falls to minus VCC. So output voltage rapidly falls to minus VCC. Now the capacitor will start to charge in the other direction. The capacitor starts to charge in the opposite direction, because the output voltage is now minus VCC. The capacitor starts to charge in the opposite direction. What happens if the capacitor is started to charge in the opposite direction? The voltage across the capacitor, the charges which are stored in the capacitor, will start decreasing. That means voltage at the inverting terminal starts to fall. The voltage at the inverting terminal starts to fall. If the voltage at the inverting terminal starts to fall, and if it becomes less than the voltage which is present at the non-inverting terminal, now the output voltage changes to plus VCC. This repeats. So you will get a continuous square waveform. This is the output of a single stage, a stable multivibrator. So I hope you have understood. Now the upper threshold voltage, that is the maximum positive value for the voltage at the inverting input will be, so using the voltage divider rule, the upper threshold voltage is equal to VCC into R2 divided by R1 plus R2. This is about the single stage stable oscillator. Here you need to understand the charging and discharging of the capacitor, when it charges and when it discharges. And also you should understand the concept of the comparator. When the voltage at the inverting terminal is more than the non-inverting terminal, the output voltage changes to minus VCC. When the voltage at the non-inverting terminal is more than the inverting terminal, the output voltage will become plus VCC. Next, crystal controlled oscillator. Whenever you need accurate frequency, then we will go for the crystal oscillator. Usually it will be a quartz crystal. That is a thin slice in a hermetically sealed enclosure, vibrates whenever a potential difference is applied across its faces. So that is nothing but the piezoelectric effect. The phenomenon of piezoelectric effect is when you apply a potential difference between the opposite phases of a quartz crystal, it vibrates at a particular frequency. That frequency of oscillation is determined by the crystal's cut and the physical size. Whenever you need accurate frequency of oscillation, then we will go for the crystal controlled oscillators. Here is a simple Jft oscillator. As you have not still studied Jft, don't worry about the circuit. This Jft is nothing but junction field effect transistor. This will have source, drain and gate. just go through the circuit because you don't know what is JFET, how it works and all. So it is one type of transistor, just like a bipolar junction transistor. This is JFET, and the terminal source, drain, gate are just analogous to emitter, collector and the base.